We turn now to the Newtonian Revolution, an event not only significant in the history of Western science, but in many ways even more deeply, an event profoundly significant in the history of Western culture. Newton arises out of the growing attraction to a larger and larger number of bright young minds in the 17th century of the kinds of inquiries invited by the new philosophy. If you think back to the very first lecture, we talked about how the whole structure of reality is conceived in that philosophical system, pointed people away from certain kinds of study as trivial and directed minds toward issues of abstract metaphysical philosophy or, ideally, of theology itself. But as a result of the cumulative effect of so many of the revolutionary currents in the world of education, learning, reading that we've discussed this far, by mid-17th century throughout Europe, one sees young men, there are no women educated at the universities, young men drawn to societies of mathematically and mechanistically oriented empirical natural philosophy. What we would now term science, so great has been its triumph, but which in the 17th century remains natural philosophy. One of the striking features of the creation of these societies is how much of it occurs apart from the universities. Though the participants are often students, graduates, occasionally professors at the universities are strictly and usually legally wedded to the Aristotelian scholastic method. And where the universities provide no home for the new experimental sciences, the new mechanical physics, the new astronomy, like-minded young men form clubs, societies, salons, often attract patronage, aristocratic, royal patronage, and create a whole set of counter-institutions in the ways that some people argue, rightly or wrongly, I leave to your judgment, but in the way that some people would argue that in the 1980s and 90s, some of the best social science is being done at think tanks rather than in departments of sociology or political science at the universities.
From the perspective of what we now think of as the mechanical sciences and physics and astronomy, the truly exciting work is being done apart from the universities in societies and clubs devoted to the new philosophy. In England, from the 1640s on, there are meetings which tend to get more and more regular of students, tutors, and professors at London, at Oxford, and at Cambridge who are interested in non-Aristotelian natural philosophy. They tend to call it either experimental philosophy or simply the new philosophy. They are a generation excited both by Francis Bacon and by the progress of the mechanistic sciences.
By 1660, the group is meeting weekly and defines itself as a society devoted to, quote, and you'll see how many of the, this is not part of the quote actually, you'll see how many of the themes we've addressed so far are caught up in the main themselves.
They say their society is one devoted, quote, physical, mathematical, experimental reasoning. One can think now again to begin more on it, criticism of philosophy. That is not by moral techniques that one will advance unit knowledge, not by experiments. And this is essential to the work of the war. Society abhors of one's experiments, so that these may be open to the examination, the attempted confirmation or disconfirmation, the criticism of others. In 1664, the Royal Society divides itself into committees that give us a wonderful flavor of what they took to be the important tasks of their group. First, there was the Mechanical Committee, dealing with all matter of subjects from physics, dynamics, mechanics, abstractly conceived, to work being done on pumps, for example, or means of measurement. There is the Astronomical and Optical Committee, interested in astronomy, interested in the development of machines to enhance and allow for observation and measurement, and interested as well in the physiology of perception and in questions of what is involved in perception and sight. There is the Anatomical Committee, the Chemical Committee, the Agricultural Committee, an important committee on the history of trade that, among other things, quite essential to the island kingdom, dealt with issues of navigation and broader issues of the increased efficiency of commerce. The Seventh Committee is one absolutely ideal for a 17th century mind or course. I shall give you its full name. The committee, quote, to record phenomena of nature unrecorded or hitherto unobserved. A committee whose official purpose embodied a sense that there was a world out there to be looked at for the first time. Phenomena that people obsessing on matters of pure theology and abstract metaphysics had never bothered to record, to systematically observe. And finally, the Eighth Committee, again very important, a committee of correspondence that linked this society to like-minded societies of people interested in the new sciences, the new philosophy across the face of Europe, creating an international community of the new sciences and the new philosophy. Despite the increasing macadamization of so much of the mechanical sciences and Bacon's suspicion in the new organon
of mathematization, of a rush to order, of imposing too much order upon the world. It is a generation dramatically under the influence of Bacon. His utopian work, The New Atlantis, which had, you'll recall, the House of Solomon, the equivalent of the Royal Society, at the very center of its being, The New Atlantis had gone through 10 editions by 1670. And in the first publication of the Transactions of the Royal Society, by which they decided to communicate to the vast reading public the fruits of their observations, reports, experiments, and research, the frontispiece of the book showed us the King of England in the center. On one side, the President of the Royal Society, and on the other side, Sir Francis Bacon, labeled the restorer of the arts. Arts meaning all applied human knowledge. Science was knowledge per se. The arts were the application of human knowledge. Hence, our faculties of arts and sciences. The Royal Society, in publishing their Transactions, finds an avid reading public and draws for its articles on combinations of some of the most deep and learned and rigorous scientists on the one hand, and what became known as the virtuosi on the other. A country gentleman farmer, for example, who would send in an article, a new recipe for mulberry wine. It accomplished many things. It drew such people into the orbit of the Royal Society, gave people good uses of mulberries, and enormously expanded the audience for works that were of a much more serious nature as well. In that first publication of the Transactions of the Royal Society, Europe met, in many ways for the first time, a figure who would be of almost unimaginable influence in terms of the shaping of intellectual culture. Isaac Newton, later to be Sir Isaac Newton, who published in that first volume of the Transactions his work on optics, in which he had, through the prism, divided light into its primary colors. Isaac Newton was the son of a Lincolnshire farmer, born in 1642, the year of Galileo's death. There is good evidence that he was intended to become himself a gentleman farmer, but in 1661 he enters Cambridge University. He's old for that, 19 at the time, but there had been a civil war in England, and many a person's education had been suspended. He enters Cambridge University and is quickly caught up in the world of higher learning. Now, Cambridge University in 1661 is absolutely dominated by the Aristotelians, but Newton enters Trinity College, and it is the one college in Cambridge where the Cartesians are strong and influential. And Newton, as a young student then, is introduced to Descartes, to the analytic geometry, and to higher mathematics. Although it will be Newton who will overturn the Cartesian physics of a universe without a vacuum, a universe that's a plenum, that's filled with matter, so that all problems of physics are problems of, in effect, fluid dynamics, though Newton will overturn, eventually, that Cartesian physics, his introduction to the new mechanical philosophy, and above all to higher mathematics, is at the hands of enthusiastic Cartesians. He is taught mathematics by one Isaac Barrow, who held the most distinguished chair in mathematics in Great Britain. In 1665, people have to evacuate Cambridge because of a visitation of the Great Plague. And Newton goes to the countryside at Woolsthorpe to await during 18 months the passage of the plague. It is perhaps the single most extraordinary 18 months in the history of Western thought. While at Woolsthorpe, Newton is thinking about a problem that many people are thinking about across Europe. The problem of the motion of the moon. The great continental natural philosopher Huygens had demonstrated to European science, in addition to his work on the pendulum, the problem of a swinging globe. You attach a globe to the end of a chain and swing it around your head, and you let go. It does not continue traveling in a circle. It flies off in a straight line. Now, almost all physics and astronomy in the 17th century, not just the Aristotelians, but Galileo's as well, you will recall, depended upon the notion that the circle was a natural inertial motion, that the circle was a natural motion. Descartes, on the other hand, purely as a matter of logic, had argued that all motion was a straight line, that everything proceeded in a uniform straight line unless acted upon by another force. But when Descartes thought about why the moon should be traveling in a circular orbit rather than in a straight line, he conceives of it as a problem of a whirlpool in a great tub of water, for his universe is full. What is the swirl of the medium of rarefied matter on which the moon rests that accounts for the motion we observe? Newton is predisposed by his familiarity with the Cartesians to think of motion as linear in its inertial sense, and he is very familiar with and thinking about the problem of Huygens' swinging pendulum, that when you let go of the chain, flies off in a straight line. And he is trying to think what would be the force that could be operating centripetally upon a moon that of its own inertial motion would be proceeding in a straight line, but is drawn as if by some invisible chain toward the center into the motion we observe. In point of fact, there is every reason to believe an apple did fall as he sat outside thinking about the problem. And Newton put to himself the case, at what point does the force operating upon the apple, by which it falls in obedience to Galileo's law of falling bodies, at what point and in what manner might that diminish? If you drop it from a hill, it drops. If you drop it from the highest mountain, it drops. Presumably then, one could hypothesize if you dropped it from much higher than the highest mountain, it would drop. Suppose that one projected that force outwards indefinitely and sought to conceptualize it as the equivalent of that chain that would be holding the moon in orbit rather than causing it to fly off in a straight, rather than allowing it by its own inertial motion to fly off in a straight line. And he arrived at a calculation that some other people had come very close to arriving at, thinking about what would be the force exerted by such a chain if one treated the moon, in effect, as a swinging globe problem held by a string. And Newton arrived at a calculation that the pull of the Earth diminished according to the square of the distance from the center of the Earth. In effect, that was the law of gravity. But not having his books with him in Woolsthorpe, he did not have the precise figures for the circumference of the Earth, calculated by miles to a degree. And his calculation was slightly off. As he wrote, he, quote, pretty nearly, end quote, proved his calculation. In fact, he had discovered the law of gravity. But his proof slightly off, he set it aside and mentioned it to no one. In that same 18 months, Newton had found it enormously difficult to work with multivariables of space, motion, and time merely with Descartes' analytic geometry alone. So he developed a means of calculation, the differential and integral calculus. In the same 18 months, thinking about the problem of motion, he developed the three laws of thermodynamics, the three laws of motion that lie at the heart of modern physics. Interested in the question, how do Galileo's abstract mass and force behave? Newton developed three laws of motion. One, the law of inertia. Matter in motion, mass in motion, proceeds in straight linear motion unless acted upon by another force. Matter at rest remains at rest unless acted upon by another force. He defined that force as the ratio velocity equals time times acceleration, and articulated his third law of thermodynamics, that for every action there is an equal and opposite reaction. Still during those 18 months, he developed whole new ways to think about the nature of numerical series, and through the prism discovered the composition of light and laid the foundation for the modern science of optics. In short, in the 18 months that followed his receipt of a BA at the age of 23 to 24, Newton had formulated the law of gravity, formulated the essential laws of motion, mechanics, thermodynamics that would govern Western physics, created the calculus, laid the foundation of modern optics with his experimental discovery of the composition of light, and absolutely typical of Newton, who often forgot to eat, He communicated not a word of this to anyone. From the 1660s to the 1680s, he was England's most celebrated mathematician, but no one knew of his work on gravity and on the laws of motion. When, in the late 1660s, he finally showed Isaac Barrow the work he had done on mathematics, and in particular the calculus, Isaac Barrow did something that never happened before, and I guarantee you never will happen after. He immediately resigned his chair in favor of his student, Newton. But there he is from the 1660s to the 1680s with no one knowing about his work on gravity or the laws of motion. In 1684, there was a meeting in a London coffee house of three great scientific minds. Edmund Halley, the great astronomer whose comments so disappointed us all, Sir Christopher Wren, the great architect, and Robert Hooke, astronomer, mathematician, and the first great theoretician of the mechanical laws of the elasticity of mass. Discussing the problem of the moon and Huygens' work on the swinging globe and on the pendulum, Newton had seen the connection 20 years before. Hooke proposed the inverse square law as a model of what the force might be. Wren thought about it and wagered that it could not be proven. Halley and Hooke put their mind to it and cannot prove it and cannot use it to account for any of the data of the observed celestial world. They think their problem might be with the mathematics, and Halley is sent to Cambridge to get the views and help of the celebrated mathematician, Isaac Newton. He asks Newton, what would be the curve produced in a satellite if there were a force that diminished as the square of the distance between two bodies? And Newton immediately answers, an ellipse. The elliptical orbits of all heavenly bodies and of the moon exactly as Kepler had maintained. Halley looks at him in wonderment. We're told, how do you know that? I'd worked it out, Newton says, but it didn't quite fit. According to one of Newton's relatives, Halley said, where did you work it out? And Newton begins looking through his desk drawers unsuccessfully. As one celebrated historian of science had noted, all of European mechanical science was looking for a law of gravity. Isaac Newton had lost it. Finally, Newton is able to communicate his work to Halley, and Halley sees at once that with the geography of the Earth corrected, the whole solar system and Kepler's planetary laws all fall into place, and that Newton has demonstrated it mathematically consistent with all observed data. At Halley's urging and expense, Newton works on his discovery, integrates it into his general laws of motion, thereby linking all celestial and all terrestrial physics, and publishes it in Latin in 1687, volume 1, the Philosophia Naturalis Principia Mathematica. Wonderful 18th century title, the mathematical principles, 17th century title, of natural philosophy, or as it is known simply, the Principia. It took him 18 months to write, and it changed a culture and the culture's way of understanding the world in which it found itself. It was, as many said, a mathematical demonstration of the Copernican hypothesis as proposed by Kepler in the three planetary laws of motion, which now, for the first time, had their experimental proof. It explained all of the then known phenomena of celestial motions pretty well by means of the supposition of a force of gravitation that decreased according to the squares of the distances between the two bodies. It made the universe seem ordered, lucid, comprehensible. It made the human mind seem capable of understanding the very architecture and design of God in the creation. It is important to understand how the culture perceived the Newtonian accomplishment. The English Catholic poet Alexander Pope penned Newton's epitaph. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. The great astronomer Lagrange, 100 years later, was asked by Napoleon, would there ever be another Newton? To understand how the early modern European world took the Newtonian accomplishments, here is what Lagrange replied to Napoleon. He said, there can only be one Newton because there was only one universe to discover. Writing in the 1730s, attempting to explain Newton to a French audience, Voltaire put it this way. He said, Descartes put us on the road to truth. Newton took us to the end of that journey. The astronomer Halley, in a poetic introduction to the Principia, concluded his verse on Newton's accomplishment with the line, "Nearer the gods, no mortal may approach." Those senses, all was light. The human mind had discovered the actual universe. We had unified celestial and terrestrial physics, had reached the end of a dramatic journey that a human inquirer had come as close by natural means in this mortal sphere as anyone could to touching the mind, the plan of God. These are as much a part of the Newtonian Revolution as any specific achievement in mathematics, in physics, or in astronomy. Posit linear inertia as a force operating en masse wherever it be in the universe. Posit gravity according to Newton's formulation, and one understood the composition of the heavens in a manner absolutely consistent with one's ability to understand and predict the motion of things on Earth. Few could understand Newton substantively. They depended upon the writers of prefaces. They depended upon popularizers. But those popularizers and those prefaces increasingly made it clear. With this model, the heavens and earth fell into place. There was mass, there was measurable force, there was space and time and distance. And with the mathematics correct, one understood the world at which we had gazed in ignorance till now. And from that system, one could predict with accuracy the planetary and celestial motions, the tides whose behavior now followed from the law of gravity itself, Kepler's ellipses, the behavior of comets. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. The Cartesians read Newton and said, "Wait a minute, this is no explanation at all. This is mysticism. We don't see the mechanism. This is as speculative as the mysterious forces given to things that can't be seen in Aristotelian scholasticism. Let's try to understand how the Cartesians responded to Newton's system, because if we understand that, we will also be able to understand a very important direction in which European science will move in the wake of the Newtonian accomplishment. If one wanted to make fun of Aristotelian scholastic learning in the 17th century, one made fun above all of their giving everything a secret reason for moving that couldn't be observed. These were called occult forces, forces that couldn't be seen in scholastic language itself. A stone fell to reach its proper place in the universe. Fire rose to reach its proper place in the universe. It had a hidden force by which it moved. In Molière's play, Le Médecin Malgré Lui, the medical doctor in spite of himself, we get a critical view of an Aristotelian scholastic oral examination for someone seeking his doctorate in medicine. The examiners ask him, "Why does opium put one to sleep?" And he answers, as a good Aristotelian, "Because of its dormitive power." And the doctors go, "Doct, learned." For the Cartesians, what kind of explanation is that? Why does opium put one to sleep? Because of its dormitive power. Let's see what happens in the nervous system. Let's see what happens physiologically. Let's study the mechanisms of the effect of opium. This is how they hear Newton. Why do the planets and moons hold their orbits? Because of their power of attraction. Beg your pardon? Because of their power of attraction. Have you seen it? No. What is it? A force that operates like dormitive power. For the Cartesians, it was no explanation at all. Imagine a universe filled like a bathtub with water and swirling motions and eddies and whirlpools, and you could understand why things moved. A billiard ball strikes another billiard ball. It communicates its motion. One understands such a thing. One looks for the mechanism by which force is communicated. But what are the Newtonians giving us? Action across a void. Action at a distance. A billiard ball moving another billiard ball without ever touching and with allegedly nothing in between through which a force could travel. For the Cartesians, it was mysticism. It was Aristotelian occult forces all over again. Action at a distance. Powers of attraction show us the mechanisms. Now, in fact, the Newtonians initially are sensitive to this. They want to know what gravity is. They try to see, could it be magnetism? But that doesn't work. And finally, they make a virtue out of a necessity in a manner very consistent, and the two, you can see them merging right here, very consistent with the Lockean model that we are limited to explaining phenomena, not what underlie phenomena. The Newtonians reply, what we have demonstrated is that such a force exists. What we have demonstrated is the quantity of that force. On the basis of that, you would predict exactly what you observe. On the basis of that, you can predict the behavior of comets and tides. We know that such a force exists. We know the quantity of such a force. Why such a force should exist, in what way such a force can operate in the universe with action at a distance, we do not know, and we will not feign hypotheses. Non fingo hypothesis, Newton will state. I do not feign, I do not make up hypotheses. Where we lack the data, where we lack the experience, we do not posit hypothetical explanations. We admit our ignorance. God is free, Newton will write, and his defenders will write. Unlike Descartes' God, who must operate the universe according to the principles of fluid dynamics, God is free to have created as he chose. God is omnipotent. We see what he has done. We see the exquisite nature of the design. We see the laws of nature. We state them quantitatively. We see through nature to nature's laws and their author, God. And we will not in science attempt to posit metaphysical and hypothetical explanations of why the world should be as it is, or how it could be that the world is as it is. We will state what we know, and we will await data before going farther. Note, for cultural conclusion, that if one could see through nature to nature's laws and their author God, this meant both that nature was knowable and that the pursuit of natural knowledge was also the pursuit of the wisdom, the design, the handiwork of God. Science was a piety. Let no one think that he was sacrificing his soul or higher faculties in the study of nature or rocks or rivers or motions. Nature reflected the exquisite design of God, and all science was a piety. But the greatest legacy of all from Newton was the sense of order and clarity, and all was light. The Newtonian achievement gave Europe a great confidence in the method which had brought about this achievement. One could argue all one wanted in the abstract. Should one be experimental? Should one be inductive? Here was the proof of what one received by this method. God did not intend us for ignorance. We now had a method by which to use our minds and know his world. And for many, this was a model to be extended to the whole of knowledge. Thank you.